Today, it gives me great pleasure to introduce today's speaker. We welcome Professor Gregor Borg, a professional economic geologist with over 40 years experience. Gregor began his career in Germany before conducting a PhD in South Africa, and is now a professor of economic geology both at the Martin-Luther-University in Halle-Wittenberg, Germany, and also at Camborne School of Mines, the University of Exeter, the most prestigious mining school in the UK. And Gregor has published a whopping 85 scientific papers, as well as numerous consultancy reports across a variety of different deposit types: uranium, banded iron formations, tin, tungsten, lithium, rare earth elements, and of course, sediment-hosted copper deposits, which we will be going over today. Gregor is also the deputy chairman of the advisory board to Deutsche Rohstoff AG, and has been involved in the discovery of 2 gold deposits, which have now contained over 3 million ounces of gold in Tanzania. So we're very privileged to welcome Gregor, who will now begin his talk on the Kupferschiefer. So over to you, Gregor.
Thank you, Jamie and Filipa. Thank you very much for this opportunity. And we have just before been talking about this marvelous technical improvement that we now can talk to audiences that are sitting all over the world, and we're getting people to discuss exciting things that excite us and that we want to have answers, problems that we come up with. And Murray Hitzman is here, and he's been listening to a Kupferschiefer talk that I gave to the SEG student chapter of Ireland, of Dublin, not so long ago. And so I was worried that it could be boring for him. And so I tried to come up with something that is most importantly not boring to me, because I've given this lecture so many times and I get bored if I give the same lecture all the time. So first of all, Murray, it's a different title, as you can see, and it's third time lucky, and I will talk about the redox yo-yo. But talking about a subject that you have been dealing with for a long time and having the danger of it being boring, a little bit boring, it reminded me of a quote that was attributed to the 5th husband of Tsasa Gabor. Tsasa Gabor was one of these divas, and she was married many times. And it's supposed to be a quote that was actually said in the wedding night of the 5th husband. And he's supposed to have said, "I know what to do, but I've got no idea how the hell am I going to make it interesting." So let me try to make my talk interesting. And you have already been looking at some of these almost iconic images of the Kupferschiefer, of the sediment-hosted copper, lead, zinc, plus other metals deposit, or this metallotect. It's a huge belt in Europe, in Germany and in Poland. And you see the various images, where I'm not going to go into too much detail. You see highly energy consuming total smelting of these ores, which typically have 2% combined copper equivalent. And you see old mining sort of guys lying on their side with a pickaxe, and you see modern mining as it is happening at the moment in Poland. And the mining in Poland is going strong. And in Germany, we still have undrilled and drilled targets. Let me quickly see. I have to switch to this one. Here we go. Okay. So we basically see that all of these mines and these exploration areas are on the central southern margin of what is called the Northwest German and Polish Basin. We're talking about the boundary. It's straddling, the metal deposits are straddling the stratigraphic boundary because lower and upper Permian. And we know this basin, which is a basin with the red bed sediments of a thickness of up to 15 kilometers. We know the sort of the stratigraphy and the contents of the basin extremely well, because there's also hydrocarbons in the basin, and that has been drilled very, very strongly. The image at the bottom left is not in Baku, it's not in Texas, it's in northern Germany in 1917. So it is drilled very, very densely. What is the Kupferschiefer? And actually, I should not call it Kupferschiefer, because that is so very, very confusing, because it implies that it's always mineralized and it is a slate, and schistosity is not attributed to this type of rock. So what do we know about it, which is stratigraphically called T1? T1 is much easier and less confusing because it's non-interpretive. We have this drill pattern, and we know that it's commonly only a 20 to 50 centimeter thick shallow marine to lagoonal sediment. And in the marginal facies, where we also have these ore deposit, it is black, it is organic carbon rich, that can be up to 15%. If it's lying on mine dumps and it's hit by lightning, it starts burning. Looks fantastic afterwards. It is typically a little bit marly, so there is a carbonate content. It has less organic carbon, which is pretty normal if you go away from the lagoonal or from the shallow marine marginal portion of this. And what is important to get away from this misunderstanding, it has no metamorphic overprint, and is most of the basin, it only contains 200 to 300 ppm metals combined, which is absolutely standard for a black shale. And the copper deposits, I should say copper, lead, zinc, gold, silver, plus cobalt, nickel, and so on, they are limited to the region that I'm showing you here. To put this into perspective, as far as tonnages and grades are concerned, there are a lot of numbers in here. But if we look at the Poland total figures down here, the metals, the million tons of ore that is still proven and probable because it is open to depth, it is 2.8 billion tons of copper ore that are still proven and probable. So we're talking about a huge mined, proven, and probable is 2.8 billion. But if you see the remaining probable reserves, they are 240 million tons. And so we have quite, and that is the probable, and the proven is 1.4 billion that is still proven. And we have obviously huge quantities of copper metal in there in Poland. In Germany, one of the areas, which is the classical Mansfeld area, of which you see an image here, is mined out, but there is something like 35 million tons of ore at around about 2% and a mining width of 2 meters still remaining as proven reserves underground. They were left over when the GDR and the GDR times mining actually terminated. But there's also a large target area close to the Polish border with 100 million tons of ore. And there are, according to an interesting exercise that I've done with the United States Geological Survey, there are another 6 or 8 partly drilled or undrilled targets that still hold potential. So we're talking about a huge metallotect with amazing pre-mining and still available reserves in there. Let's have a look at the stratigraphy. Now we're having the stratigraphy here on the left-hand side, and on the image on the right-hand side, we are lucky enough that we have an outcrop where, due to faulting, the deeper footwall in the red beds is in contact to the stratigraphy that we're talking about. On the left-hand side, we see all of this is in the Permian. We've got the red beds of, they call the Growligand, which is the red footwall, because that was on in the lower half, and we have the Zechstein, which means the tough rock, which is the limestone, which was a tough hanging wall above the ore horizon. Now, don't be mistaken, the T1, which is the black shale, yes, it can be mineralized, but the mineralization can be from 60 meters below the T1 up to 250 meters above the T1. So you see, it's a big zone that can be mineralized, and the mineralization can be from the red beds, from bleached red beds, from dune sands, through the black shale, to the limestone, and even to the overlying anhydrite. So it is obviously not just a planar flat earth theory mineralization. It has been studied for a long time, and in this list here, 1815 is the oldest one in here, and we have got some rather recent ones in here, and you see almost every model has been thrown at it. So from sedimentary to epigenetic to magmatic, very crazy one. It's basically mud brine volcanism and massive sulfides pouring out of a vent and so on, to SEDEX, to early diagenetic, late diagenetic, and multiphase. I'm not going to go into this in great detail. What I'm focusing this time is not my standard structural geology plus the Kupferschiefer story. I will focus on 3 individual redox events. And then there are a few more features, as structure always plays an important role. So what was the situation in the lower Permian? These are images from Namibia and from the United States. And we're in Nevada here. And we have a red bed environment, desert type of environment. Everything is under oxidizing conditions, terrestrial. Plus we have some bimodal volcanism. We have got some basalts, we have got some rhyolites because it is a failed drift type extensional environment. We've got some evaporites in there. We've got some halite and we've got some gypsum. So there is chlorides, there is sulfur, there is chlorine, and we've got iron 3+. So it's hematite, goethite and hematite, a terrestrial oxidizing environment. What happened towards the end of the Permian? I'm showing you this map over here, and you can see this basin, which was basically pretty close to Death Valley. That means it was a terrestrial desert basin, which was below the sea level. And this basin became flooded. It became flooded to the Ferrer Rift, the Viking Graben, and the Carpathian Graben. And it got flooded. And then this is an example of flooding of a desert environment in Namibia, in the Namib Desert, where 35 kilometers away, rain was falling. And all of a sudden, this desert environment in a wadi got flooded in a flash flood. Quite impressive to see this. Everything is still oxidizing. But what happens if you have such a big pool? It's basically like a pool without a filter, and you've got a water depth of 5 to 10 meters. It is stagnant, and it is in an area where there's no hinterland with rain. So you're ending up with a big mud pool. And this mud pool starts to stink. There are some fish in there. The fish are not feeling well. It becomes euxinic, and you're ending up with a stinking lagoon in which all of a sudden you have your first redox event. All of a sudden you see, except for the hair of that one student over there, which still looks like red bed color, so there's bright red, everything else is gray or black. That means we have the first redox event. We form framboidal pyrite in the sediment in there, as you can see in this beautiful image from David Rickard. And when you dig into this black mud, there is sulfur, it starts stinking. So we have our first organic carbon-rich mud. This is also a sink. It's a sink for any metal that is in the environment and that is dissolved. So you precipitate during high water, from the marine water, you will precipitate metals, but you don't form an ore deposit. Now, the second event that happens almost simultaneously, and even simultaneously to the flooding of the desert, is that this water will penetrate into the loose sand, into loose terrestrial sediments, into the red beds in a downward descending manner. And this now is sort of, you can call this a very, very, very early diagenetic process. And you've got chemically reducing fluids that descend into the red beds, and they are bleached. So they start to get mottled at the border, they start to get bleached, they get white, they get gray, and they form something that people mistakenly have labeled as stratigraphic units for a while. And they called it Growligand, which is the gray footwall, and Weißliegend. Actually, the Weißliegend are actually dune sands. So all of this is bleached in a very, very early diagenetic manner, but after deposition of these red beds. So we've got our redox event number 2. It is not a stratigraphic unit, and it has an irregular lower boundary, which is understandable if we understand the process. Before I come to the third redox event, let's first have a look at ores. We are here to talk about ores. We want to see rocks, we want to see metals, we want to see ores. So we've got 3 types of ores here. These are examples from Poland. On the bottom right, we see quite an impressive one. This used to be a white dune sand. Now, why is this white dune sand bluish and purple and violet and black? Because it has been impregnated, and the carbonate cement has been replaced by bornite. But not only that, some of the feldspars and even some of the quartz has been replaced by bornite. So that is a very, very odd thing. And that can't have happened in a sedimentary process. In the middle, we see some vein type, not surprising. It's a carbonatic sandstone, which has partly been impregnated next to the veins. And at the top left, we see the replacement of the carbonate cement in a beautiful sandstone where you have fining upward cycles plus a dewatering structure. And there, obviously, the coarser bases have more chalcocite mineralization than the fining upward cycles in the upper portions. And obviously, these are epigenetic replacements. If we go to the carbonates in the hanging wall, and this is a couple of tens of meters up into the hanging wall on the top left one, you see a nice carbonate rock. And the carbonate has been brecciated. There are veins and breccias. And obviously on the veins, there is chalcocite and bornite, and there is replacement of carbonate. And on the right-hand side, you see a footwall replacement of white dune sand from a cross-cutting vein. And again, a replacement of this type can only have happened after lithification of the rock, after carbonate cementation. That means we're talking about epigenetic mineralization. If we have a look at some of our sedimentary framboidal pyrites, and there's a beautiful photograph on the right-hand side from one of my students, it almost looks like sort of this famous South African and Californian grapes, but these are all originally framboidal pyrites, and some of them are completely replaced by chalcocites, and some of them are halfway replaced, some of them are still pyrite. And on the left-hand side, you see a picture by my good friend Sławek Oszepalski from Poland, and he shows in an ore microscopy image that you have a framboidal pyrite, which used to be pyrite. They only form from pyrite. There are no primary original copper iron sulfide framboids. They're always pyrite, but it has been replaced by chalcopyrite. And you see that there are only sort of cores of remaining pyrite in there. And that means the copper comes in a later stage. Two more examples. On the right-hand side, you see carbonate replacement of chalcopyrite. It's almost massive sulfide there, but it's replacement. And on the left-hand side, you see a vertical veinlet, and you see bornite and chalcocite filling the veinlet and replacing a limestone vein, a calcite vein that is actually adjacent to that. And obviously, replace it. And this is one of my favorite ones. We're looking at the stratigraphic boundary between the T1. You've got the black organic carbon-rich shale at the top, laminated. And yes, there are some seemingly laminated chalcopyrite layers in there. And you see the uppermost gray, bleached, now reduced clastic conglomerate. And you see some of the clasts in there. They look almost like the Witwatersrand pyrites and chalcopyrites, but there is no chalcopyrite in the Witwatersrand. They're pyrites. And here we see chalcopyrite, chalcocite clasts, pretty well rounded. And they are replaced. And what is replaced in there? It is the feldspar and the mica. The quartz has not been replaced. And obviously, that is an epigenetic event. Now, the question is, if we go to a bigger scale, where is the ore? Now, I go to one of the very impressive examples from Poland, and this is from the mines of Sirosowice and Rudna mine. And what we see here are some sections. We see some vertical sections from boreholes. And we see that we have the upper unit, which is the upper Permian limestone, the Zechstein limestone. We see in orange, we see the footwall conglomerates and clastic sediments. In some of the boreholes, we see the T1, which is the dark brown unit that you can see over here. Interestingly enough, in these two, there is no T1. So the black shale unit is not present either because it was a higher ground, it was never deposited, or it has been eroded. Now have a look at the ore grades. The ore grades are sometimes in the hanging wall, just above the black shale. Sometimes they are straddling the black shale, both in the footwall, in the black shale and above. And sometimes there are a couple of meters below. And as I said, they can be up to 20, 25 meters in the footwall and up to 60 meters in the hanging wall. So that doesn't look like sedimentary mineralization. There's also something in pink on the left. That's an alteration zone. And now we're coming closer to our third redox event. And this is what is basically observed in underground operations, and this is what is observed in drill hole. And that is what the old medieval miners, they were the ones that coined the phrase Rotliegend, which is now a stratigraphic term, the red footwall, and the Zechstein, the tough hanging wall, and the Kupferschiefer, yes, but they gave another term. They had the term rote Fäule. It's again one of these words with an umlaut in there. Literally translated, it means red rot. Why did the miners, and it's a redox front. And you see an impressive image from Saskia Meissner on the bottom right, from one of my students. You see it in hand specimen. And you see some mottled sort of, again, it's not a sharp boundary on the bottom left where a sandstone has started to become oxidized. And it can also be brownish like in the limestone at the top right. And it is a lateral and vertical redox front, which is always spatially and genetically related to an adjacent copper zone, a lead zinc zone. And in front of the lead zinc zone, you don't have any mineralization. You go into a pyrite zone, which has been unmineralized and unmodified. So that is what we're dealing with. And the red rot is an alteration front. Why did the miners call it the red rot? They had a very negative connotation to this, because as soon as they came from the copper zone to the right-hand side in that cross-section, the ore grade would be gone. It was absolutely barren. And secondly, it was not a stable hanging wall anymore because it had been modified, it had been altered, and it would crumble. So they didn't like this at all. And this was sort of one of there are earlier publications and mentioning of this, that this was an epigenetic effect and a redox front. But Johannes Rentsch, 1974, he was the first who published this very nice cross-section that shows what's going on there. In detail, if we look at this, we basically have a redox front, and this egg-shaped thing is moving laterally and ascendingly through the stratigraphy. The S1 are the sandstones, the T1 is the Kupferschiefer, the Ca1 is a carbonate. And basically what we're seeing is a dynamic system in which before this epigenetic fluid approaches and arrives, we have in the parent rock, we have pyrite. So if we just imagine that we're sitting in a little space and time capsule, and we're sitting next to one of these pyrite framboids, and we're seeing what's happening, and the fluid arrives, then obviously the most mobile base metal, the zinc, is approaching. So initially we have our syngenetic pyrite. What happens then? The pyrite framboid is replaced by zinc, by sphalerite. And here we have got a remnant of a framboidal pyrite, which still has a core of sphalerite, which was the first phase of replacement. But again, in turn, it is being replaced by galena. Yeah, so this is by lead sulfide replaced. So we've got an example from there. Then we go into the copper zone, and we still see remnants of our pyrite, still with a sort of a coral on the outside here, outer rim of pyrite. And we see it has been replaced by bornite and chalcocite. And if we go a little bit further, we are out of the mineralization and we go into the hematite zone. We go across the redox front, and here we've got our third event. It's epigenetic and it's laterally migrating, and it was ascending upwardly. When did this happen? Now, fortunately, there's absolute age dating. Now, first we know, and people agree, that the sedimentary age of the host rock of the black shale, at least of the T1, is approximately 258. There's a little bit of a variation. There are various techniques, and there are various publications, bigger ones and smaller ones, but in general, all scientists agree on this. Now, the mineralization ages, and there is, interestingly, there are two ages, and they have been dated with paleomagnetic dating of the redox front. There was some earlier publication that had a different age. They had to be corrected. And at the moment, there is no better method and no better data available. But we have two events, 149 million years, which is late Jurassic, And we have a 53 million years early Eocene. And I had to go and talk to our historic geologist and talk to him about the stratigrapher, what's happening? And he said, well, 149 is the opening of the North German basin. We have tilting, we have big fractures, we have big faults. And Philippe Mouchet, certainly, he was the one, I think, that connected big structural units in Europe through big supra-regional fault structures and said, look, fluids can migrate. They can connect these, and they are typically vertical, they are long, and they can actually interlink these various units. And then we've got another event at 53 million years in early Eocene, and we have plume-induced rifting in the upper Rhine-Graben. We have some hotspot magmatism, and we get some interesting mineralization, which is characterized by a different metal association. It's more on veins and breccias, and it's dominated by cobalt and nickel, which immediately points to a mafic, ultramafic source. But why is it where it is? It's not in the entire basin. We go to the British part of this basin, there is nothing. We go to the Cologne, to the lower Rhine embayment, we've got a little bit of lead zinc mineralization. We go to Lithuania, and when we go to Sweden, we don't have anything like this. Why is it here? Now let me try to do this in very, very simple strokes. Now the first one is that the deep basement, the crystalline basement, is the mid-European crystalline zone. And the mid-European crystalline zone has this arcuate shape, exactly like I've done here, or roughly you might say. And it's a former active continental margin which has an endowment of ore deposits. So it's very, very fertile source rock. Number two, we've got the marginal fascias of the T1. So we've got a sandstone footwall, we have a black organic carbon-rich pyritic shale, and we've got a carbonate hanging wall. In the northern basin, in the lower Permian basin in northern Germany and Poland, we also have a volcano sedimentary filling. We have red beds, we've got evaporites, that means we've got complexing agents like sulfur and chlorine. And we have a dewatering of this basin upward to the south. It's an asymmetrical basin with a steep slope on the northern side and a more shallow slope on the southern side. And the typical dewatering should be towards the south. Now we also have within this basin, we have bimodal volcanics, which could be an additional source. By now, I think it's only a minor source, but it is an important source. And we have the basalts and we have the rhyolites. The basalts are good for copper and zinc. The rhyolites are good for zinc and lead. And the red beds are also good for zinc and lead and possibly for some gold. It can all come from there, plus the basement. Very important, we've got fracture patterns. We've got faults roughly at what you see here. There are conduits for metalliferous fluids. And especially if you tilt this entire package or you put some pressure or some extension on this, you get seismic pumping and the fluids can migrate. The fluids can also put up convection cells, and obviously from the heat flow, and they can transport, they can store, and they can expel metals, especially at the intersections. And we also have some cobalt-dominated, probably intrusion-related hydrothermal mineralization at the southeastern and at the southwestern portion of this entire thing. So we're ending up with the mineralized areas, which is roughly indicated by this lens over here. That's the reason why it's here. Slowly coming to the end of my talk, let's have a look at the same in cross-section. I'm just summarizing this very quickly. So we've got our red bed basin with very, very deep sediment filling. We've got the volcanics, we've got evaporites, high rate of evaporation, and the sediments are coming from an eroded basement and hinterland. And we also see indicated in sort of gray-green the mid-European crystalline high. Then we're getting this flooding that is around about 258 million. We've got this very, very rapidly euxinic Kupferschiefer sea. That is our first redox event. And the second one is almost synchronous, but it's obviously a second event to the already deposited red beds. It's the descending bleaching of the red beds, turning them into gray beds. But none of this has anything to do with ore forming event because the mass balance simply doesn't work. 149 million years. Maybe you want to tilt the screen. Maybe this entire is tilted. All you do is tilt it by 0.3 degrees and your fluid start moving. Maybe it is a tilting and the fluid moving sideways, but in the end, they're coming from the red beds, they're going through the gray beds, they're going wherever there are some former dunes and some islands, sand islands, like in the North Sea nowadays. The fluids use these as valves. They are hindered by the black shale because that is a permeability barrier, and they will react because they've got pyrite. And you have a very, very beautiful metal zonation from copper to lead to zinc. Zinc is the most mobile and moves furthest, and it moves most upward. And we know it has moved up into the Vera and hydrite. That means even before absolute age dating, the Vera and hydrite must have been deposited. Otherwise, it couldn't have been mineralized with zinc. So this is our epigenetic ore formation, the first stage. And then we apparently have a second, even later, 53 million year event, in which some of the fluids that come from local intrusive bodies, mafic, ultramafic, there is some related volcanism at the time with this. You get this type of vein type ores, they call it Rücken, which is a minus term, which is completely distracting from the fact that it's actually vein type and breccia type. And it has a markedly different cobalt, silver, nickel bearing flavor. So that is basically the last stage. I was promising that I would show you some of the unanswered questions. Basically, it reminds me of leftovers, but they are pretty tasty leftovers and they are overlooked, like the misspelling in questions, as I see. They are overlooked and these questions are still not answered yet. So you're welcome to study them. I think there are 3 or 5 PhD studies in this. So what about the replacement? Obviously, if the ore, like in the polished section on the left hand, in the thin section on the left-hand side, you see that the opaque minerals, that they are sort of blotchy, sort of blobs in there, but they are also replacement calcite veins. Now, there are calcite veins. That means there must have been a diagenetic event that first forms calcite cements and also calcite veinlets to be able to replace calcite veins. Secondly, there is replacement of feldspar and mica. And what are the conditions for this? What is the timing? What were the fluids of this? This is from a publication from 1967 from Ludwig and again Johannes Rentsch. And he's describing also what they called the sandstone ore, in which you have replacement of feldspar, but there is also a replacement of feldspar in clasts, like you see on the right-hand side. There's a lithic clast, which is partly replaced by calcite. The outer rim, wherever it's feldspar, it is replaced by calcite. And in some places, the calcite in turn is replaced by sulfides. And they are also describing that there is feldspar replaced by sulfates. Now, none of this has been studied in modern terms. One has to see whether one can find these historical sections or go and take new samples and start hunting for similar phenomena. And I'm not going to go through the details here. This is just a little bit sort of just to kickstart a discussion on this. What are the conditions? What sort of pH do you actually need to dissolve the feldspar? And sometimes even the quartz in some cases. And I showed you this blue sandstone, the dune sand from Poland that was replacing even the quartz in there. You need very, very odd pHs for that. What about carbonate? What about sedimentary fluids? What about diagenetic fluids? What about epigenetic fluids? So there is plenty of work that needs to be done and that can be done. And the most important thing is we need to maintain our curiosity. You have to remain curious. There are questions, there are projects, there are theses to be written, there are papers to be written, there's research to be carried out. Go ahead with it. And that brings me to the end of my talk. Thank you.
That is absolutely brilliant, Gregor. Absolutely fantastic talk. Really, really well explained. Okay, have we got any questions then, Filipa, while I explain that?
Yeah, we got, but I would like to call today. We have Murray and Philip, Murray Itzman and Philip Muches will join us for this discussion. So I would like to call them and see if they have any question for Gregor or any comment on this talk. Murray, if you want, you can start. Sorry.
Great, thanks. So Gregor, nice talk. And I have a lot of the same questions you put up. I'll throw one back at you, and I doubt you know the answer, but it'd be really cool to try and find out. So especially with where the quartz and the feldspar grains are getting replaced in these Kupferschiefer type systems, and the same thing happens certainly in Kazakhstan in those systems as well. Has anyone ever mapped the intensity of where quartz is being replaced in a deposit system?
No. That is, it's a very good question. It's add that to the list of what needs to be done. It has been ignored, and I have to go back. As I said, I mean, you've seen that paper by Ludwig and Rentsch was from 1967.
Yeah.
And when you talk to these old guys, then all of it, I mean, you had the psychological problem that in former East Germany, they're living metallogenically, they're living in this flat earth. Everything was in sedimentary to the point that the GDR miners would leave behind the hanging wall ore because it was not supposed to be there. Okay, and there is, if you go to the literature and you talk to the old miners, they all say, yes, we have one type we call Sanderz, sand ore, but that has nothing to do with the Kupferschiefer, they will tell you. So no, it has not been mapped. And I mean, it's an intriguing phenomenon. And I mean, if I go and jump completely to a different ore deposit type, and you have published on the supergene zinc deposits, I have images and I've published them in Scorpion mine. There we know that it's a very, very strong acid from the oxidation of the pyrite and of the sulfides. And I have pictures where you have the famous Arcos at Scorpion, which has completely been castified, has completely been eaten away, both the feldspar, the quartz and the mica, and it's absolutely amazing. You've got a hypercast in there. And what makes it even more complicated, I talked to Hans-Martin Schulz at GFZ in Potsdam, and he said, well, the fluids coming from the red beds, at least the ones that they are measuring today, they are not acidic. So how do we explain what's happening? And no, I don't have an answer for you. Just more questions. Philip.
Thank you. Philip, yes? I checked the box. Yeah.
Yeah. First of all, thank you very much, Gregor, for a very, very interesting talk and a very nice overview of. I will still call it the Kupferschiefer deposit.
Yeah, I know.
It's a term which will take some time to abandon it. One aspect, and it's also a question which will come back in the questions of the colleagues. It's about the source of the metals on the one hand, which I see the cobalt, the rare earths, and the uranium I saw as questions in the chat. And of course, it's not only the source of the metals, it's also the precipitation conditions, which are different, for example, for the different elements, such as uranium is different from the cobalt. But I leave these questions for you, but it's a related question. So I want to frame the question a little bit with regard to the questions in the chat. An important aspect for all ore studies is indeed looking at the source of the metals. It's an enormous deposit, as you very nicely have shown. It's enormous amount of copper, and then we're still not talking about the PGEs, for example, which are there and so on. But are you able to quantify by a mass balance the possible sources of the different elements? And I would like to focus on the copper first, of course. Do you know the thickness of the sediments in the whole basin? Do you have an idea about the copper content of that basin? And is that sufficient in total to produce the amount known in the southern part of the basin? So is the Rotliegende sufficient as a source for the copper? Or do you need a source from the basement And it's a general question in many sediment-hosted copper deposits. It's also valid for the copper belt and deposits in Canada and so on. So it's an important question for the Kupferschiefer, but also very relevant for all sediment-hosted ore deposits covered, but on the, if you go further also for zinc and lead. So do you know if the mass balance fits, or do we need again more data?
Okay, I mean, obviously it's one, the source question is one that we can discuss for quite a long time. And it's an extremely valid question, obviously. First of all, and I've been working off and on the Kupferschiefer for quite a while. I was first sent by my PhD supervisor from the Kalahari Copper Belt. Before I actually went to South Africa to do my PhD, I was sent, he gave me a budget, Ken Maiden from Australia, and he sent me to Poland. And I published a paper very early on comparing the Kalahari Copper Belt with the Polish Kupferschiefer. And I was sort of hooked on the idea that it was because in the Kalahari Copper Belt, at least in the Namibian part and also in the Botswana part, you have also bimodal volcanics. And I was hooked on the idea it was the basalts. The basalts actually are obviously a very, very nice source for the mafic part of the metal suite. So for the copper, for the zinc, can be for the gold and so on. And I published this paper and I said, look, if I just do a very, very simplistic modeling of the volume of the basin. So to come to your final question, no, I haven't modeled it. It hasn't been modeled. I think it is possible because there's so much drilling data. So one can have a balance, and certainly it doesn't balance for the seawater. That is the one thing I believe at least. So I was thinking that it was coming from those basalts, and I presented it. And there was at the time one of the directors of the Polish Geological Survey. And at the time, it was a very sort of still very dogmatic guy. And he said, no. The basalts, they have drilled them. They can't be the source. They only have 30 to 40 ppm copper. Well, the range of copper in basalts, and I did quite a bit of work on that in my career, is variable. But if you want to have an average number, then you're talking about 200 to 350 to 400 ppm. That means what he was referring to was a depleted basalt. So certainly the basalt has produced some copper. And what I always say is all fluids, scavenging fluids, are stupid. They pick up any metal where they can. If they have chlorine, if they have sulfur, they are aggressive, they are nasty, they negotiate with any rock that comes in their way. So obviously, when they can, they will strip the basalts of their copper and their zinc and their gold and their cobalt, whatever is in there. They will also strip the cave feldspar in the red beds because they are very, very immature clastic sediments, and they carry lead. So obviously, we have a lead source, and again zinc from the micas and so on. Plus, we've got this basement underneath, and I think I have much more now. I'm much more, if you want me to give from a gut feeling, not from modeling, not from calculating, I would say 55% probably comes from the basement. And the rest comes from somewhere between 40 and 60%. I'm easy to have my arm twisted on this. You could also say, well, that can only be in shear zones and faults, therefore the volume is less, but it's very fertile. So all of that together, I think, can supply this. Also the palladium, especially from the mafics, that's the classical and typical source that you can get from there, both from the basement and from the basin volcanics. That's basically sort of the closest I can come, and no, it hasn't been modeled yet.
Thank you.
So
Opens the.
I can jump in. Can you hear me?
Yes.
So the first paper I ever published on sedimentary hosted copper, I think, was on exactly this question, Philippe. It was a terrible paper, by the way.
I know the paper.
Yeah, it's bad.
Well, we all agree. Sorry about that.
No, that's fine. So I've worried about this my whole career, the source. I think if you actually do a calculation with the volumes that are supposed to be present of the Growligand and compare them to average red beds, source of the copper is not a problem. probably source of the lead too, because of the K-spar, and zinc is all over the place and all sorts of elements. So I don't worry about that. I think there's probably plenty of source. I actually happen to agree with Gregor that as I've gone on through time, I've become more of a basement enthusiast. And mainly, excuse me, mainly that's because the ore fluids are clearly very dense and want to sink, and they're going to sink into the basement. So they interacted with the basement, I think is pretty clear. I worry much more about things like cobalt. So, you know, I cannot explain the DRC and Africa with why that district is so cobalt rich. And while there's a huge volume of cobalt in the Kupferschiefer, if you take it all together, the actual, you know, grades are very, very low, right? So, but what's also interesting is Africa has almost no silver. The African copper belt is depleted in silver. It's anomalously low, right? So most of the deposits in the world are copper silver deposits, really. Sedimentary copper, that's what they are. They produce those two metals and other things too. Africa is somewhat unique. There's other ones like Kazakhstan that have other metals, germanium, rhenium, other things too. But I think we have to start thinking in groups of metals, and again, how they vary through space. So in Africa, we have a pretty good idea where the cobalt-rich areas are, where the copper-rich areas, where the nickel-rich, the uranium, etc. In the Kupferschiefer, I mean, the poles may have the data, but I haven't seen it. We know that there's parts of deposits that are, say, gold-rich or palladium-rich, but regionally, you know, this is a question, I guess, for Gregor. So do we have the gold and palladium rich zones that we know of in Poland? Do those exist in Germany too?
Well, let me put it this way. Gold was recovered during GDR times, but it's quite, I mean, when we're talking about sustainable mining and that we should finish our sandwich and don't leave half of that uneaten. GDR was absolutely amazing by extracting whatever was possible in there. It was both uneconomical and it was unecological, but they needed the stuff to buy Forex. So you had rhenium, for example, and in some cases they would produce over 30 years, they would produce 6 kilos of XYZ. Yeah? The total amount is not very high. Metallogenically, it's interesting, is in there. There are in the Mansfeld and Sangerhausen area not these rich gold zones, but when you go to the area to Spremberg-Weißwasser, which is close to the Polish border, there is a gold-rich zone, which unfortunately is higher up in the stratigraphy at a distance. So you might have problems mining that together with it because it might become uneconomical. So when the further you go east, you have local flavor. Let me put it this way: you have local flavor. Now in East Germany, it is more a vein type local cobalt, although cobalt was systematically be recovered. But what we are seeing, for example, in our modern projects on the mine dumps of low-grade ore, I mean, they were called low-grade ore, they're 2.5% copper equivalent. And on average, cobalt is nowadays not recoverable under economic conditions.
Awesome. We have a hand up from Holger Portek. I wondered if you were going to add to this discussion, Holger, so you can unmute yourself.
Excellent. Hi, Gregor.
Hi, Holger.
Best regards from Vienna, from the Geological Survey. I very much enjoyed your talk. Thank you very much. I was really looking forward to have you explain to me and most part of the audience how the Kupferschiefer ores actually came to be into existence. And what I really liked about your talk was that you put that into a good model in the end, putting all the pieces on a regional scale into the picture that sort of shows why it is where it is. But on that point, I got myself wondering whether that is a completely unique geological situation that you are describing, or whether you could extract exploration parameters that would be able to be employed in the search for, well, Kupferschiefer type ore deposits elsewhere. And that would be question one, I guess. And the other question that was going through my mind was that you were highlighting the importance of the mid-German crystalline rise in the subsurface of the whole system. And I wasn't really quite sure if I understood how critical that was to the formation of the ore deposit. And I understand, hopefully correctly, that in essence, the Kupferschiefer is where it is because the T1 was forming a redox boundary type trap for the upcoming fluids to deposit the metal load at the location where it is today. So, yeah, thanks for the talk, Gregor. That was
thanks, Holger. Excellent questions. Let me start with the last one first. The T1 is also a permeability barrier. So you will have, when fluids sort of either through thermal buoyancy or through tilting of this entire block, they will sort of hit a barrier, which is not impenetrable, where you have faults fluids can migrate through. And quite interestingly, if you look at the Northern Sea, at the North Sea, you see this chain of islands. And they are basically sand dunes that people now go and have their holidays on, and they build their houses on. And they're complaining when the sea level rises and so on. And they are basically, when you put sort of a black mud around them, they stick out. That means later on they are valves, but still the T1 is a hydraulic barrier, and that will slow down fluids, and the fluids will pond. And you need this sort of barrier for more residence times to do all the replacement. But you're right, you understood it correctly, that you have this sort of reactive horizon, plus you've in the upper part, once you go into the carbonate, you obviously have a buffering effect of the carbonates. That means all of a sudden you're in a carbonate replacement deposit environment. Okay, and obviously the ore types and the textures, they look exactly like a carbonate replacement type deposit. And if you're in the sandstone ore, and that was why these people, they were saying, well, this has nothing to do with the Kupferschiefer. Well, it has all to do, because your ore textures depend on the host rock. And coming back to that part of your question, yes, I think it is dominantly the underlying fertile mid-European crystalline high with all of these rock types and former deposits that were in there. But your first question that came to what can we find out as exploration criteria? Well, I think it is fertile basins need source rocks, but in the end, source rocks, you find them in most basins. That is not the big problem. It's nice on your tick-off list to have them in there. Yes, that is fine. You need structure, because these are not sedimentary deposits. And in the end, you need conduits, you need funneling structures, you need focusing phenomena, you need intersections. And if I didn't show this, Murray saw it in my last lecture 4 or 6 weeks ago. Where are these ore deposits in more detail? When you zoom in, this is a zoom talk, but I can't zoom in at the moment. And you see, it's at the intersections. And the ore deposits, the mined ore bodies, not the ore deposits, the mined ore bodies, they are following these intersections, sometimes beautifully. And even that has not been modeled. Even that has not been modeled because people said it has nothing to do with the Kupferschiefer. So there was big sort of a mindset that was hindering this. When you come to the more, let's say, the less obvious ones, it is look out for redox events. And I'm not talking about stratiform redox events. Either big regional ones, these clouds, this fluid cloud that come basically start studying and looking at roll front deposits. Roll front deposits are very, very similar. They are just very, very low in copper, lead, and zinc, although it is there. and they are normally explored for and mined and leached for the uranium. The uranium is in the Kupferschiefer, and obviously it plays its role in the metal zonation. It's all there, it's just the proportion are different. So study and have a look at roll front systems. The other thing is, I was fortunately enough to help Anglo-American and a Danish exploration company that was exploring in central eastern Greenland. And there you also have evaporites in the basin, you've got red beds in there, and all of a sudden you see vertically cross-cutting bleaching. You see redox events where red beds are all of a sudden whitened. And you go to Utah, you go to these fantastic areas where you got these beautiful red rocks, and you've got salt diapirs, and you see fluids that have on the margin of the salt diapirs, and you've got hydrocarbons in there, and they're going upward and they're hitting barriers and they're mushrooming out. And that's one of the interesting things. The classical phenomena in our profession is that salt geologists don't talk to ore geologists, and both don't talk to oil and gas geologists. And that's why we stay all stupid. Sorry, that was a bit blunt, but I mean, we can all, what I'm saying, turn it around. We must be curious, and we must talk to these people across these discipline barriers. Yeah? And I think that is what is so far. I've suggested it to people. People wouldn't pick it up very much, but that was normally because the project was seized. But I think look out for these odd redox events, these epigenetic redox events. Try to find out what's happening to these fluids, to the salt-related fluids and to the hydrocarbon-related fluids.
Awesome. We did have another hand up, and it was from, I think it was James Davey. I don't know if you wanted to still come in, James, or if you're even still here. If you are, you can unmute yourself and sort of say if you want to say something.
Hi, Jamie. So, well, I mean, Murray basically covered what I was going to say, and I guess the conversation somewhat moved on now. But I will just say, great talk, Greg. I really enjoyed it. Yeah, the only comment I was going to make was on the metal sources. You know, I guess the volume of source rock and therefore the metal inventory needs to be kind of taken also in the context of what fluid we have available to move the metals. And it sounds like perhaps, you know, we're not as advanced in characterizing those fluids in the Kupferschiefer as perhaps we are in some other basins, but certainly not all. So yeah, that was my only point. And I think in, you know, looking at it in the Central African copper belt, you know, as Murray alluded to, I think it's become clear there, although although there's certainly no preclusion of a basement source, I don't think you necessarily need it just from a mass balance perspective to provide at least the copper, as Murray said.
Mm-hmm. All right, then. Thanks for that, James. I
think Murray wants to respond.
No,
okay.
I actually want to ask a question of both Gregor and Filipa, because I'm interested. So the Kupferschiefer, I mean, it's a very large interior basin. And we know it has copper, you know, the copper marls in England, etc. So it provided a redox trap, which trapped metal, but only in this corner of the Poland, Germany area did it apparently make ore deposits. Now, you know, a lot of the other area is buried, and so, you know, it's not as well explored, obviously. But why? How do you explain that one corner of that basin is well mineralized and the others aren't?
Well, it basically depends on what's on offer. So if we go from this copper province to the west and we go to the city of Cologne, we are in the lower Rhine-Graben that goes into the Netherlands. And it has been studied by the team from Günther Friedrich and the guys, and also Willem Putman on isotopes and on the organics in there and so on. They did quite a lot of early work on there, and it is you have sub-economic mineralization, but it's all lead zinc, lead dominated lead zinc. And that fits to the Rhenish Massif. And then we're coming pretty much to Philippe Mouchet's homeland and the mineralization that you're finding in there. You've got vein type and breccia, lead zinc. You've got lead zinc that became supergene modified and so on. Yeah, you go to Kelmis and so on. So it's a different province. It's a different province, and that is even further support, I think, that you get a basement source rock connection to this copper province, which is away from the Rhenish Massif, which is with the typical lead zinc barite veins. And you come to this mid-European crystalline high with is not enough drilled, so we don't have the understanding as well as in other parts of the world. That's, I think, the reason why. You asked the question about the northern shore of this basin, and just for the audience, I repeat it here. I think the reason is that you had you don't have the mid-European crystalline high as a basement, number one. Secondly, you have an asymmetrical basin with a steep northern margin and a more shallow southern margin. That means your typical dewatering or even recirculation fluids in there is more towards the south. And then probably also had some tilting, and that is more in the field of Philippe, he was the first one, and I think it's one of the key papers because he linked the various big crustal domains in Europe. And he said, look, if you have these big faults, you can link the fluids. I mean, it's not sort of taking them from here and you form an ore deposit there, but you're linking these big units. And I think that is also something where more research can be done on to follow up on that.
I just can comment that there are two factors already, and there are probably many more, but I think still the Growligand is coming from the rocks below anyway. Yeah? It's reworking. So even if you look for the source in the Growligand, you still have to know what's below in the basement. So there is anyway a connection which you're just explaining, Gregor. I'm just repeating. And then the second point is, what you well explained is the focusing of the fluids, and there could be dewatering towards the highs. There could be faults facilitating the fluid movement, and indeed, it's the combination of the processes. It's what I refer now as these days as a word is system thinking, and looking like other people talk like the basinal approach done by the oil industry, and that's what we all should consider, and I'm sure Murray can convince this, confirm this, because I heard him many times also talking about this broad approach and looking at all possible factors to find an ore deposit. And as you said very well during this talk, don't pick up one model, don't pick up one precipitating mechanism, fluid flow mechanism, but look at all factors, and then you come to a good prospecting deal, a question which we had already earlier.
Cool. Okay. Filipa, do we have? I suppose we can move on to some of the other questions in the chat now, right? Sorry, Filipa. I was going to just ask. This is a question. This has been sitting there for a little bit of time now. So apologies to Michael, but this is focusing more on the cobalt and rare earths. This question. So it says, what is the geochemical content of cobalt and total rare earths in ppm in the Zechstein limestone and the Kupferschiefer? Is the redox front enriched or depleted in these metals? Thank you. I think we covered a little bit of this, but
that's a very quick one. I don't know. now, first of all, I mean, one would have to go and dig into the literature regarding the cobalt. But as I said, I can't answer it here. There is a huge wealth of literature that one has to dig through. There is no rare earth element anomaly or contents in there that is worth mentioning. Uranium locally, yes. The uranium is also very local and very strongly structurally controlled. And anybody who wants to go to the labor to dig through the literature, our Kupferschiefer paper from 2012 in the Dixilito volume has an electronic appendix. We have something like, I think, 6 pages of references in print, but there is also an electronic appendix of I don't know how many more other publications in there. So the information might be in there, should be in there. In Poland, it's not so easily available, but I can't answer the question offhand.
No, that's absolutely fine.
Okay, fair enough.
Murray did kind of say in the discussion that the cobalt's pretty low-ish in the in the Kupferschiefer, especially in comparison to.
Comment on that. Now the question is, when we say Kupferschiefer, what are we talking about? Are we talking about the black shell-hosted one that is extensive? Then I agree completely with Murray. It is low. There is an ore type that is in the westernmost West German portion, which is called the Richelsdorf Mountain, which is close to the cities of Kassel and Fulda. And there they have what they call Kobaltrücken. Now, Rücken is a miner's term for a ridge. Yeah? It's like the back spine or a ridge. And they were called cobalt ridges. Why? You're walking until today through the forest and you find an elongated ridge. And it is the silicified Gossen, and that has typically erythrite. And you can find beautiful pieces of the bright pink arsenates and cobaltates. Yeah? So you find cobalt, you find arsenic, and it's typical vein type. Now those were not low-grade ores, they were rich ores, and they were mined as vein type. And people would say, but they've got nothing to do with the Kupferschiefer. Complete bollocks. Yeah? They all come together. And depending on what rock type you go, it looks different. Yeah? And for decades, people, and for example, you have to go back to all the publications from the big armada of people that were working in the Harz Mountains and in the Thuringian forests on vein type mineralization. And they were dating, they were doing ore microscopy, and it had nothing to do with the Kupferschiefer. Now, all of this has to be brought together. And you might find that all of a sudden the 149 and the 53 is not such an isolated event. And in my normal talk, and Murray might be remembering this, there is a very, very nice graph from David Leach in one of his papers. And in there, you find in the Cevennes, you find in Ryocin, you find in southeastern Poland, all of a sudden, the two events, 149 and 53, are also there. It all has to be synthesized. It has to be brought together.
Awesome.
Okay, great. We have a question from the YouTube, so I would like to read it. So the question said that in Carlin gold deposits, the supportive quartz grains are required to maintain fluid pathways during carbonate leaching and mineralization. Is there any equivalence in the Kupferschiefer deposits?
Again, it might well be. I mean, one can only invite people from other type of deposits, at least in a first step, to go to the literature. Some of that is very old literature, some of that is Polish, some of that is German, but it hasn't been checked. So it might be that phenomena that are pretty well known from other type of deposits are there, and they simply have been overlooked. You only recognize what you know. That's one of the very, very wise sayings. So you might overlook it easily because it hasn't been explained to you. I mean, this is just a lot of bullshitting around. I can't answer the question. I don't know. So yes, it's worth testing. It's worth studying. That's what I wanted to say. Maybe one of the things to the gold zone, where it is in a systematic manner. It is very, very close to the redox front, and it is actually in Poland, it's on the oxidizing side. It's on the fringe, but it's very, very close to the redox front, but on the oxidizing side. So there is some work by Henry Kucha on this, and also on the palladium and platinum. I'm not quite sure about that one. It has never been reproduced, but the gold is pretty well documented also by Adam Pistrinsky. He has done quite a bit of work with his team on the gold mineralization. One last question.
Okay, thank you. Yeah, I think
that has covered all of the chat's been done.
Yeah.
And I think all of the YouTube's been done. I mean, it's quite an interesting question, and it's certainly a question about fluid pathways and sort of the lithological controls potentially on that. And I think that's a really good point you raise. There's lots of processes that happen in other systems that could potentially be equally applied here. So yeah, definitely worth researching that. I don't really have any questions myself. A lot of them have been answered during the discussion. I don't know if you have any like a roundup question, Filipa.
Mary, I think, has still one.
Oh, okay, we can end on that then.
Yeah,
Well, no,
go ahead.
It's a question sort of for Philippe, but it's addressing the last question. So in Carlin systems, you're absolutely, the questioner is right. That is one thing that happens. In these systems, I think it's potentially more complicated. I haven't done petrography on the Kupferschiefer much at all. I've looked at a couple hundred sections, but I can't pretend to really know what's going on. But for Africa, what I can say is, the Rotliegend equivalents, the lower Rhone, had a very complicated history. So, it went through periods where there was certainly feldspar dissolution, feldspar growth, overgrowth, recrystallization, carbonate dissolution, carbonate precipitation, and quartz dissolution and precipitation too, through time. And so I totally agree that understanding how fluids actually are maintained in this what seems to be a pretty dynamic situation, obviously extending over millions and millions of years, right? So we have lots of time. But how we do that, because those changes obviously are telling us that the fluid chemistry is changing, right? That's what they're implying. So we do have real changes in diagenetic to hydrothermal to brine chemistry through time, and then at least in some situations they seem to repeat. So we actually have cycles where we're going through and we come back to a similar chemistry. I think that whole space is one that has not really been studied. I mean, I think it's very fruitful for things going forward. Yep. I think there's a lot there to learn.
Absolutely right.
Okay then. Well, in that case, I think on that bombshell, as the Top Gear presenters used to say, we shall end the talk there. Thank you for everybody that has stayed around and has attended this session. Big thank you to you, Gregor, for giving your time and providing a really interesting and fruitful presentation. It's been a really interesting discussion for sure. And hopefully everybody that's attended today will join us in the future, because we've got more events coming up across the summer and across the year as well. So it's goodbye from me.
Thank you very much for the invitation. It was really good fun. Thanks for the discussion. All that Mary, Philip, Holger, that was very interesting, and all the other questions that were raised. And keep well, stay safe. Kaiko, good to see you, at least briefly. We were exchanging emails a little bit earlier on today. Good to see you. Yes.
Okay,
all right.
Thank you very much. And again, thank you, Murray and Philip, to join us. And thank you, Gregor. See you in 2 weeks. Bye-bye.